Real exam questions. The exam question 40, Ultimate Limit State General. Determine the reduced bending moment, mu d, and the position of the neutral axis xi of the boundaries of all domains where simple bending is possible. Make a sketch of these domains indicating the most important values of the strains of concrete and steel, and this for concrete quality smaller than 50 megapascal. So we start first with the unloaded section, and we look at the strain diagram. So on top, we got the concrete strain, epsilon c. On the bottom, at the distance d, we got the strain in the steel, epsilon s. And the distance between two is the effective depth d. The maximum compressive strain of the concrete is epsilon cu2, which is 3.5 per mil. And the maximum strain in the steel, we have limited up to epsilon ud equals to 10 per mil. Now, we are looking up all the regions where simple bending occurs. Well, it starts here. If you have a strain diagram doing this to the left, then you do not have any compression in the concrete, so it cannot be simple bending. So that's the first. Then, of course, this is also simple bending with the compression height. And this is the other limit for simple bending, because when the region coming after it to the right, which is the region 2b, is not possible, because then you need a normal force to make the equilibrium. So we have region 1b, 2a. So that are the two regions with simple bending. Now let's look at the different limits of those regions. Let's take first this region here. The diagram of forces. You have the total compressive force in the concrete, and at the bottom the total tension force in the steel. The distance of between them is of course d minus delta gx, but we are writing it in dimensionless units. So this distance d, if you divide by d, you got of course 1, and then this is delta gc, and c is x over d. Again, dimensionless units, then you know this is CC, which is the total concrete component, filling coefficient, and point of gravity. And making an equilibrium, a rotational equilibrium around the tension reinforcement, you have, of course, CC, this times the value here. Now let's consider the first limit of the region. We know this is applicable. And for this line A, of course, x is here 0. So that means C is x over d is 0. And when C is 0, then mu d is also 0. So for this line, we have C and mu d, all of them are 0. Of course, this point does in reality not exist, because you cannot have theoretically an equilibrium. Only when this goes a little bit to the right, then you can have bending. Then for line B, for B, then we have to look for x, the value of x. This value of x is, of course, the 3.5 per mil divided by the 13.5 per mil. And it gives you this portion, which is x over d, this is c, and that's 2.259. We can use this formula to calculate mu d, and we find 0.187, which is okay, because this is the strain diagram for optimum use of the materials. And then we go to the right border, C, and for C, you see that the X is equal to D, so C is 1. And we use this formula here, with C is 1, and we find 0.473. So for bending, mu D will be between 0 and 0.473. Otherwise, you cannot have simple bending.